Hello everyone. The topic for this video is Blackbody radiations, Wien's law and Stefan's law. Let's get started. Okay. So the first one is Blackbody radiations. Now, for A-level physics, what you need to know is a body that is capable of absorbing all the radiations. So none of the radiation is reflected back. Okay, so two things you need to write. One is the one that absorbs all the radiations falling on it. No reflection is happening, no transmission is happening. So it absorbs all radiations and then emits all radiations at higher temperature. So if it is heating up, it will absorb all the radiations. I'll give you an example. Let's say, for example, there is a metal filament, okay, and you're heating it up by giving it all possible radiations. The temperature is, let's say, 10 degrees Celsius. So it absorbs all the radiations that is falling on it, and the temperature increases to, let's say, 100 degrees Celsius. All right, so now it is not absorbing all the radiations. You have stopped this. Now what it will do is, because it is at 100 degrees Celsius, it will start emitting all the radiations it has absorbed. So it does not keep anything to itself. Whatever it absorbs, it emits. It absorbs at lower temperature and emits at higher temperature. So whenever you have an exam question, you need to specifically say that it absorbs all radiations falling on it and then emits all the radiations back. So this would be a typical exam question. What is meant by a blackbody radiator? A body that is capable of emitting and absorbing all the radiations. Now, why is it a good emitter? Obviously, because it's a good absorber. It has absorbed all the possible radiations, so it's going to emit all the possible radiations. So what you can write for this one is a good absorber is a good emitter. And because blackbody is a good absorber, it absorbs all the radiation, therefore it is a good emitter. Now, next thing what you need to know to be able to read and understand what blackbody radiation curves are. So this one that you can see on your screen is a typical blackbody radiation curve. Now, how to read this? First, let's see what's on the y-axis. So this is a graph between intensity of any radiations, okay, how intense the radiations are, and on the x-axis, I don't know how come it's not visible. So this one is the wavelength. Okay, so wavelength of the radiations. Now, and as you can see, at different temperature, there are four curves here. One is drawn at 5000 Kelvin, 4000 Kelvin, and 3000 and 2000. So one inference is very clear. As the temperature decreases, it flattens out. It's not tall. So the curve, curve becomes taller as temperature increases. Okay, so this is one inference from this curve. All right, let's see the next one. What is happening to the wavelength? Now, to the peak wavelength, so at the wavelength at which the curve peaks. Now see this one. This is peaking here, this is getting peaked up here, a peak here, or a peak here. So obviously the wavelength is decreasing. The wavelength, not all the wavelengths, okay? So wavelength when intensity is maximum. Now this is a very important point. Don't say maximum wavelength. So intensity, when intensity is maximum, that particular wavelength decreases with increase in temperature. Decreases with increase in temperature. And now also, what is not clear in this graph is the area of the curve. Now, as the temperature increases, the area under the curve increases. So area will give you the total energy radiated. Total energy radiated increases. How do you know that? As area under the curve increases with temperature. Increases with temperature. That's I hope we got that. So what's happening here is, once again, as intensity is increasing, intensity increases with the increase in temperature. Larger the temperature, taller is your curve. The peak of these curves gives you the wavelength. The wavelength associated with the peak of the curve decreases as the temperature increases. So as you can see, the peaks are shifting towards the left. And because it is becoming taller, the area under the curve, which gives energy radiated, it also increases. Now, this then leads to something called as Wien's law. So what it says is, what we have understood in the previous one, that wavelength of maximum intensity, okay, not maximum wavelength, but wavelength of maximum intensity is decreasing with temperature, is it not? So see, 30,000 Kelvin, 5,500 Kelvin, 1,000 Kelvin, and what's happening to the wavelength of the peak intensity? It's shifting towards left, going towards here. So this wavelength and this wavelength and this wavelength is going more and more towards the visible region, is inversely proportional to temperature, of absolute temperature. Inversely proportional to, absolute temperature. I'm going to write in mathematical form now. So lambda associated with maximum intensity is written lambda max, but it's not maximum wavelength. This lambda associated with maximum intensity is inversely proportional to absolute temperature. And when we remove proportionality, we have a constant small b over t, which is known as Wien's constant. And Wien's constant is dependent on the nature of a substance, which substance you're taking. So just the value here, then the value is 2.9 10 to the power minus 3 meter Kelvin. So B is 2.9 times 10 to the power minus 3 meters Kelvin. That's it. That's your Wien's law. So Wien's law is clearly from the graph that the maximum wavelength, I said the same thing. Wavelength associated with maximum intensity decreases as temperature increases. This could be one of your exam questions when you are reading the graph and understanding what's going on. Let's just see. Two blackbody radiation curves for A and B. So first I'm going to the graph and seeing A and B. Curve A has a higher peak and is shifted to the left. So obviously, because it's shifted to the left, the wavelength is less, temperature is high, energy emitted is high. So 3 marks here. Point number 1, point number 2, point number 3. A has higher temperature. So that's the first reading because it's taller. Second, lambda max, that is the wavelength of maximum intensity radiation for A is less than that of B. And of course, who emits more energy? Star A. Star A emits more energy. Generally, this is the third mark is the mark which generally students end up not writing. Emits more energy as area under the graph is increasing, is higher for A. Okay. As always, whenever you're doing a question, you should pause, don't wait up for my answer. You do it yourself and then check. Every single mistake you make is the mistake that teaches you. If you do not make mistake, there's no learning. All right, let's start. So this is again one of the simple exam questions, which would be a part of a bigger question, of course, or it'll be a multiple choice. A star has a peak wavelength. So peak wavelength means the wavelength associated with peak intensity is 500. Small n is nano. You get rid of the nano by timesing it this. So you have to find the temperature. So I'm using lambda max is B over T. Rearranging, T is B over lambda max. 2.9 times 10 to the power minus 3 divided by times 10 to the power minus 9. And if you use your calculator, let's see how quickly I can do that. All right, not happening. All right, give me a second. All right, so my answer is 5800 kelvins. That's about it. Okay, now let's try another one. Okay, that's the answer. Now the third thing today is Stefan's law. Now what this gives us, now we have understood in thermal physics that a particle is, the kinetic energy of a particle is given by 3 over 2 kT or half kT. Now for a particle it is half kT. Now if all these particles are forming a big body, how much total energy would that big body radiate if the temperature is increased? As temperature increases, the kinetic energy of each particle increases. It undergoes more collisions with each other neighboring particle and then would emit more radiations. So this is, so L here is a symbol for luminosity of a star, and it is also nothing but the power emitted. The power of a star or any body at any temperature T and area A is given by this equation. So what these things are, so L is the power of a black body or a body which is similar to black body, like our sun or a star. Okay, then A is area of that black body or the star, whatever you are taking or question is giving you, and then T is absolute temperature. That means the temperature in Kelvin. So what it tells us, and this sigma here, this symbol is called sigma. This is a constant, Stefan's constant. I'll tell you its value in a minute. So Stefan's constant, now it's a constant. So what this equation is trying to tell us, that if temperature increases, temperature of any black body increases, let's say temperature of a star increases, the power shoots up. Okay, because power is directly proportional to the fourth power of temperature. A typical exam question, absolute temperature is doubled. What will be the change in the emitted power of radiation? So it will be doubled to the power 4, 2 to the power 4, that is, it will become 16 times. So can you see how hugely the power emitted changes once the temperature changes? All right, so I'm going to just explain you in terms of photons theory what's going on here. Question later. So when the temperature increases, I'm going to just write it. Wait, let's just add another slide. Get us free page here. All right, I'm going to just add another. Okay. So as temperature increases, what is happening to the photon energy? Temperature increases, wavelength decreases. Okay, we just did Wien's law. That means the frequency emitted would have increased. Now the photons that was making up your radiations, EM radiations, the photon energy is increased. Okay, so the energy of each photon is increased, and then because you have a huge number of photons emitted, the power of or power emitted would also increases sharply. So that is what is happening inside the black body or inside the star in terms of wavelength, temperature, frequency, and energy. Yeah, let's just try this question. Go ahead, pause it and try to do it yourself. If you have done it, I'm just solving it right now. So a black body radiator at this much temperature. So temperature is 3000 Kelvin. It's already absolute. I need no conversions. Calculate the peak wavelength. You'll see this word peak, but always remember this is the wavelength associated with peak intensity. So this is B over T. So 2.9 times 10 to the power minus 3 divided by 3000. So that would give me 2.9 times 10 to the power minus 3 divided by 3000 is approximately 9.7. So my wavelength associated with maximum intensity is 9.67 10 to the power minus 7 meters. So I got the wavelength, first part done. Find the average kinetic energy of a particle at this temperature. Now average kinetic energy is half kT. Okay, now this one comes from thermodynamics. Okay, so half kT. If it is moving only in one direction, but remember it's three-dimensional, so we have to multiply it by 3. So it's 3 over 2 kT. There's no worries, it's there in your equation sheet. So average kinetic energy is half kT times by 3 over 2 kT, and then you plug in the value of K is 1.38 times 10 to the power minus 23 times temperature, again should be in Kelvin. This gives me the average kinetic energy. So it's 6.21 times 10 to the power minus 20. Let's just write it here, 6.21 times 10 to the power minus 20 joules. So this is done. If the temperature doubles, by what factor does the total power radiated increases? So third one. So radiated power is sigma A T to the power 4. This is doubled, so 2 to the power 4, that is, it becomes 16 times. All right, did not tell you the value of sigma here. So the sigma is a Stefan's constant. You have this value in your equation sheet, but nevertheless, so what you need to remember though is the unit. Sometimes we end up making mistake in the unit. So it is 5.67 10 to the power minus 8. Now see, the unit would be, this is in power, watts, and then area divided. So if I have to calculate sigma from here, this would be written like this. So what's the unit? Watt per meter square, Kelvin to the power 4. That's your sigma. Okay, a lot of words which are famous on the YouTube, sigma, 6, 7 and whatever. All right, so we get it. That's it. I think that's all I'm doing today. Only, yeah, what's this? Okay, we're not interested. So the three things: Blackbody radiations, Wien's law, and Stefan's law. They are very simple. Only thing you just need to know them. And mostly the questions from Stefan's law are, if there are multiple choice, they would be asking you temperature is doubled, power becomes 16 times, temperature is tripled. So 3 to the power 4 is 81. So power become 81 times. Temperature is halved, power would become 1 over 16th. So that's all you need to know. All right. So well done. Keep revising. I'll see you soon. Thank you.